13.5. Gravitational potential energy. The outline of this video is as follows. We are going to develop a more general expression for gravitational potential energy, one that works even when an object is very far from a planet. First, we will quickly review the simpler formula we have used so far, which is only valid near the Earth's surface. Then, we will derive the general formula, paying close attention to our choice of a reference point where potential energy is zero. After establishing the new formula, we will examine its important properties. We will then see how to apply this concept to find the total potential energy for a system containing more than two particles. Finally, we will work through an example to confirm that our new, more general expression correctly simplifies back to the familiar mg delta y for small changes in height near the ground. Let us begin by recalling the expression for gravitational potential energy you are already familiar with, and discuss why we need a more general version. From earlier studies, you know the potential energy of an object of mass, m, at a height y, is given by the equation U sub g equals m times g times y. This simple formula is very useful, but it relies on a key assumption, that the gravitational field is uniform. That is, it assumes the value of g is constant everywhere. This assumption is only valid for situations close to the Earth's surface, where changes in height are small compared to the Earth's radius. However, we know that the gravitational force is not constant. It weakens with distance according to an inverse square law. To analyze things like satellites or planets, we need a potential energy function that reflects this change. Therefore, we must derive a more accurate expression for gravitational potential energy that works for any distance between two objects. Let us now derive the general formula for the change in gravitational potential energy. Our starting point is the fundamental definition. The change in potential energy is the negative of the work done by the conservative force, in this case, gravity. We want to find this change as an object moves from an initial radial distance, r sub I, to a final distance, r sub f. First, we substitute the expression for the gravitational force, which is negative g times the mass of the Earth times the mass of the object, all over r squared. This force is directed radially inward. When we place this into the work integral, the negative sign from the force law cancels the negative sign in the definition of potential energy. This leaves us with a positive integral of 1 over r squared. Performing this simple integration and evaluating it at the limits r sub f and r sub I gives our final result. The change in potential energy is equal to negative g MEM multiplied by the quantity 1 over r sub f minus 1 over r sub I. To assign a specific value to gravitational potential energy, we must first choose a reference point where the energy is zero. While this choice is arbitrary, the standard convention is to set the potential energy to zero when two objects are infinitely far apart. This is a logical choice, because the gravitational force between the objects also becomes zero at that distance. Applying this convention to our previous result for the change in potential energy simplifies the equation. When we set the initial potential energy to zero at an initial separation of infinity, we are left with the general formula. The gravitational potential energy of a particle Earth system is U of r equals negative g times the mass of the Earth times the particle's mass, all divided by r. This expression is valid for positions at or outside the Earth's surface, where r is greater than or equal to the Earth's radius. The key result is that gravitational potential energy is a negative quantity that approaches zero as the separation becomes infinite. Now that we have a formula for gravitational potential energy, let us explore its key properties, especially the meaning of its negative sign. The most important feature is that this potential energy is always negative for any finite distance. This is a direct consequence of our choice to set the potential energy to zero only when the two objects are infinitely far apart. Since gravity is an attractive force, the system naturally has less energy when the objects are close together compared to when they are at infinity. Because the force is attractive, an external agent must do positive work to pull the objects away from each other. This work gets stored as potential energy in the system. Therefore, as the separation distance r increases, the potential energy also increases. Since it starts from a negative value, increasing it means it becomes less negative, moving closer and closer to zero. Do not confuse this with the force. The gravitational force varies as 1 over r squared, while the potential energy varies as 1 over r. In short, for any two objects bound by gravity, their potential energy is negative and increases towards zero as they are pulled apart. Now let us extend the concept of gravitational potential energy from a simple two-body system to a system containing 3 or more particles. This is crucial for understanding the dynamics of things like star systems or satellite constellations. To find the total potential energy for a system with multiple particles, we simply calculate the potential energy for every unique pair of particles and then add all of these energies together. This is an application of the superpositional principles. For the 3-particle system shown, the total potential energy is the sum of the energies for the 3 distinct pairs. We calculate the energy for the pair of particles 1 and 2, then for particles 1 and 3, and finally for particles 2 and 3. The total potential energy is the algebraic sum of these 3 individual terms. This total value has an important physical meaning. Its absolute value represents the total amount of work required to completely disassemble the system by pulling all the particles infinitely far apart from each other. In this example, we will show how our general formula for gravitational potential energy is consistent with the simpler version, mg delta y, which we use for objects near the Earth's surface. We begin with the general expression for the change in potential energy that we just derived, which states that delta U sub g equals negative g m sub e m times the quantity 1 over r sub f minus 1 over r sub I. Our first step is purely algebraic. We will simplify the expression by combining the two fractions inside the parentheses. Finding a common denominator of r sub I times r sub f gives us a single fraction. After we combine the terms, we can absorb the negative sign from the front of the expression to flip the order of the terms in the numerator. The result is that the change in potential energy equals g m sub e m multiplied by the fraction r sub f minus r sub I over the product r sub I times r sub f. This rearrangement prepares us to apply our physical approximations. Now we will apply 2 key approximations to show how our general potential energy equation simplifies to the familiar one used near the Earth's surface. This is a crucial step that connects the universal law of gravitation to our everyday experience with falling objects. First, for small displacements, the change in radial position, r final minus r initial, is simply the vertical height change, which we call delta y. Second, if both the initial and final positions are very close to the Earth's surface, then both r initial and r final are approximately equal to the Earth's radius, r sub e. Therefore, their product is approximately r sub e squared. When we substitute these approximations into our equation, the change in potential energy becomes g times the mass of the Earth times m times delta y, all divided by the radius of the Earth squared. We can rearrange this expression and notice that the quantity g times the mass of the Earth over the radius of the Earth squared is exactly the definition for g, the acceleration due to gravity at the surface. This substitution recovers the well-known formula, showing that the change in potential energy is approximately m times g times delta y. Let us explore the limits of our mgy approximation with a what-if scenario. At what height does this simple surface equation accumulate? a 1% error compared to the more accurate general equations? This is a practical question for something like an upper atmosphere probe. First, we need to know which formula gives a larger value. The surface equation assumes the acceleration, g, is constant. In reality, g decreases with altitude. Therefore, the mgy formula will always overestimate the true change in potential energy. To find the point where this overestimate is exactly 1%, we can set up a ratio. We will divide the potential energy change from the surface equation by the change from the general equation and set this ratio equal to 1.010. As shown, we then substitute the mathematical expressions for each term into this ratio. This gives us an equation that relates g, the radii, and the universal gravitational constant, g. Setting up this ratio is the key step to quantifying the error of our physical approximation. Let us continue our calculation to find the height where the simplified potential energy formula has a 1% error. First, we substitute our specific positions into the ratio from the previous slide. The initial position, r sub I, is the Earth's radius, r sub e. The final position, r sub f, is the altitude delta y above the surface, so it is r sub e plus delta y. Next, we replace the surface gravity, g, with its definition, the quantity g times m sub e, all divided by r sub e squared. When we substitute this into our ratio, the g, m sub e terms cancel out completely. The expression simplifies nicely to the fraction r sub e plus delta y all over r sub e. This is equivalent to 1 plus the ratio of delta y to r sub e. Setting this equal to 1.010, we can now solve for the unknown height. Subtracting 1 from both sides shows that the ratio of delta y over r sub e must be 0.010. Multiplying this by the Earth's radius gives us a final height of about 63.7 kilometers. So the familiar formula, mg delta y, is accurate to within 1% for altitudes up to roughly 64 kilometers above the surface. Let us summarize the key ideas about the general form of gravitational potential energy. The potential energy, Ug, between two masses, m1 and m2, separated by a distance r, is given by the equation Ug equals negative g times m1 times m2, all divided by r. This formula relies on a standard convention where we define the potential energy to be zero when the two masses are infinitely far apart. Because gravity is an attractive force, this means the potential energy is always negative for any finite separations. For a system with more than two particles, the total potential energy is found by simply adding up the potential energies for every unique pair of particles. Finally, it is important to see that this general formula is consistent with our earlier work. For small changes in height near the Earth's surface, the change in this general potential energy, delta Ug, correctly simplifies to the familiar expression m times g times delta y. The key takeaway is that gravitational potential energy is negative for bound systems and is calculated by summing the contributions from all pairs of masses. To wrap up, let us consider two review questions to solidify your understandings. First, imagine an external agent pulls two masses apart, moving them from an initial separation r to a final separation of 2 times r. Is the work done by this agent positive or negative? And as a result, does the potential energy of the system increase or decrease? To answer this, think about the direction of the gravitational force and the direction the agent is pulling. Then, look at the formula for gravitational potential energy, U sub g, and see how the value changes when the separation distance r is doubled. Second, let us think about why the potential energy, U sub g, is defined to be negative. This is a direct consequence of our choice for the 0 point. What would be the physical implication if we made a different choice. For example, what if we defined the potential energy to be zero at the Earth's surface, where R equals R sub E, instead of at infinity? How would this change the potential energy value for an object in orbit? Pause here and work through these questions.